Okay, hello everyone. After a couple of weeks away, we're back with another video, and this is on the subject of canonical data and the importance of having just one place where any piece of data is stored and the sort of problems that you can run into if you don't have just one place where every piece of data is stored. So I'm going to show this in a simple example in Fortran, and a bit later I'm going to show it in a less simple example also in Fortran. The reason that I am showing it in Fortran is because of the fact that my later example is one that's nice and simple and I can show it quickly, and it's something that people actually do in Fortran and can cause you problems if you're not careful. But this is something that can happen in any language, any way of programming a computer, and is in fact particularly common in certain areas that are not what you'd normally consider as a programming language, that I'll sort of mention after I've shown the simple example. So first of all, to the simple example. Okay. So it's very simple. Just do that so I have my syntax highlighting right. So I'm just going to create a very simple bit of numerical code which does something that is far simpler than anyone would ever normally do, but something a bit like this is something that can happen inside other working bits of code. So I'm going to create two parameters. Okay, I'm going to create three, the first of which is just a precision parameter, but never mind that one. So I'm going to be working with 64-bit real numbers, which is why I define this one. And I'm going to define my first parameter. I'm going to call pi, and I'm going to call it 3.141. That's a value for pi. It's not a very good one, but it is a value for pi. And quite often people will work with something like that if you just want to put pi in your code. I'm now going to introduce another one, which is a trick that a lot of programmers use because it's a very easy way of getting a comparatively high accuracy version of pi without coding one in, which is I'm going to create a parameter which I'm going to call pi2, which is 4 times the inverse tangent of 1. Now that is a trick you may or may not have come across. It's one that's worth knowing, and basically tan of pi by 4 is 1. You can write 1 exactly, so you can do a tan of 1 multiplied by 4 and you get a value for pi. It's not actually perfect. There are numerical reasons and sort of algorithmic reasons why it's not perfect, but it gives you a very good estimate for pi. So, you know, that's a good, quick and dirty way of getting pi if you want it, you know, to high accuracy if you want it. Okay, but I now have two versions of pi. And what I'm going to do now is I'm just going to print the arccos of 0.2 times pi, and then I'm going to divide that by my pi2. And you can immediately see why this is a problem. And if I compile it and run it, you can see I do not get back 0.2. I get back 0.199962273, whatever. Now, that is not a numerical precision thing that the computer is causing. If I use the same value of pi for both, even if I use the wrong one, I get back a very good value of pi, much closer. And if I use the one that's actually nearly correct, I get actually exactly the same value on this machine. I got a slightly different value on a machine when I tested this earlier. But the point is, there we go. That's right. I should have put in that this should be a double precision number. There we go. We now get an extremely good value for pi, of 0.2 back out. What you were seeing there was me mixing single and double precision, which is a whole other video, but something you absolutely shouldn't do. But the point is, by having those two values of pi, this one here that's low accuracy and this one here that's higher accuracy, I actually got a worse answer by using the mixture of the high accuracy and the low accuracy than I did using the low accuracy one twice. And I'll just show by putting these back in that once I fix that double precision, single precision error, I once again get an extremely good version of that value back. So That's obviously very silly. You would never do that. Except you can. You would certainly never write this code where you just have two values of pi and you mix them up. Nobody would ever do that. It's insane. But you can accidentally do something like this if you don't just have one canonical, one true value for pi that your code uses everywhere. And this isn't something specific for pi. It's specific, obviously, for physical constants. If you have the speed of light, you don't want to be using 3 times 10 to the 8 meters per second, which is a good but incorrect approximation in one place, and 298, whatever the actual number is, I can't remember, in another place. You want to have one source that says, in my piece of software that cares about the speed of light is this. And if you then want to have any connection with reality, you want it to be the same as the real speed of light. But that's a whole other question. But this is the point. And it doesn't just apply to constants. It applies to all information. What you want to have is every piece of information is defined only in one place. You don't want to have the same thing that's meant to be the same piece of information in two places. And the reason is essentially the same thing that you see in this really rather silly, rather trivial example that I have here. What happens if they are not the same at some point? If you store the information in one place, obviously it's always going to be the same wherever you use it. If the information is stored in two places, it can in various ways become different, and that is a bad thing in general. It will usually cause a problem sooner or later. Even in the best case scenario that you manage to keep them synchronized and there's never a problem, you still have to keep them synchronized. So as a general rule, you want to make sure that every piece of information that your code is stored once and only once, and that is called a canonical the canonical store, the canonical value, the canonical version of that data. Now, this is something that's a thing in normal programming, like I say here, in a normal language, and it doesn't matter whether you're in Fortran or C or Python, all the same sort of thing can happen. You can clearly see how you could write this code in C or in Python. In Python, there's a value for pi built into the language, which might mean you wouldn't do this, but if you did, you'd get the same problem. But it's actually much more common when you're thinking about databases, where it's a lot more tempting. So in a database situation, imagine a situation where you are storing people's payment information, say. Not something you do in academia usually, but in sort of commercial use for a database, it wouldn't be terribly uncommon to want to store someone's payment information. And that will include their address. But you also have the delivery information, which will also include their address. Now, in the real world, I'm just going to gloss over the fact that someone may have their credit card registered at one address and want the thing delivered to another address. That's a complication here that's not really worth thinking about. The point is, if you assume those things really are the same, you do not want to have someone's address in the table that stores the payment information and another copy of their address in the table that stores the delivery information. What you would want is to have just one reference to the address, and then from either of those other tables you can go, okay, I can get this person's address from the one canonical source. So, and you can see exactly the same sort of thing could happen. You could easily wind up with a situation where you're able to successfully validate someone's credit card because all that information lines up, but then you deliver it to where they lived before they moved or something like that. So mistakes can happen. And I'm now going to show another example in Fortran, which is something that people really do. It's not as pathological as this. And it's something that causes problems. And I'm going to show this one in Fortran because it's a nice, simple problem that's very tempting because of the way Fortran works. And this is to do with arrays. So Fortran's a very good language for arrays. And what you might quite often want to do is have a type. I can just call T1 here, which contains an array which has a size that's only known at runtime. And I'll call it E1 and B1. I'm vaguely thinking of an electromagnetic solver here, but never mind. And what you would also then have is an integer which says the number of grid points that you have. And then I'll end my module. Except I'm not actually going to. I'm going to create a couple of subroutines. And I'm going to create, this is a parameter that's going to allocate one of these T1 objects. I should really put intents on these. I'll do that. And then what I do would be something like tin %nx equals n, allocate tin %e1n b1n. Okay, so that is a function that allocates this E1 and B1 and makes NX match. Okay. Oh dear me, what have I managed to do there? I appear to have managed to catch a key that stopped Vim from working. Okay, I'll create a new tab and we will get back. Okay. Okay, so we haven't lost anything thanks to Vim working quite well. Okay, so that's now a perfectly good function. I will now create another function which reallocates an existing one. Okay. Now, I'll just copy these. Fine. So, that should now be n sub new. Okay, so I'm now going to make a mistake, and on something of this complexity, it's fairly easy to see the mistake that I'm making. But I am just going to deallocate the existing ones, and I'm then going to allocate them to the new size. Okay. Now, in reality, a function like that would almost certainly be something that would, reallocate it to a size, preserving the content, but it's, not really worth my going to the trouble of describing that for a quick demonstration like this. Okay, so I'm going to use my module, and I'm going to create an instance of my type. I'm going to call t, and I'm then going to call alloc t 123. Okay, now I'm now going to print that nx value, and I made a slight mistake there. That shouldn't be nx, that should be n there. And I'm also going to print the size of E1. Okay, I'm now going to realloc t to 234 instead of 123, and I'm going to do the same print again. Okay. Now this is quite a long and complicated code for doing live, but it seems to compile, and I compile it and I run it. And here is the thing. So the first one, after the alloc, I get the same thing. My nx variable that stores the size of my array and the actual size of the array match. But because I made a mistake when I implemented realloc, they don't. So basically, the the thing I've done here is in this realloc, I should also have set tin%n equals n new. That's what I should have done. I forgot to do it. I made a mistake. But the point is, because in Fortran, the size of the arrays is something the arrays know intrinsically, I shouldn't have this extra variable, this nx here, storing the same information, because here it is the same information. Now, there are cases where it wouldn't be the same information. In reality, if this was an electromagnetic solver, I would almost certainly have some extra cells at each end of my array that are not real. So I'd use that nx to say how many of the cells are real and how many are not real, and work out how many are not real from the size of the array. So at which point that is just a bug. But if you're not in that situation, if you really aren't storing something that is additional information that you might need, you don't want to have it, because you can get bugs that are strange and can oftentimes look peculiar. Now, in this case, for example, it's a wonderful example, because what I'm left with is an array, something that tells me how big my array is. It's smaller than my array actually is. So if I don't make that update and run through, the code will run fine. I will never run out, access outside of memory. I'll never do anything that's programmatically invalid. It just won't do what I expect, because of the fact that I think my array is smaller than it actually is, because I don't have that single canonical source of information. So that's a very simple but potentially real problem. This is the sort of thing that is very tempting to do. You store the size of an array in a type with the array. But in Fortran, you don't need to do that. If I was doing the same thing in C, I would need to do that. So this variable here would then be the canonical source of that information, which isn't to say it couldn't still be wrong, but at least I now wouldn't be in the situation where I don't know which is real. Of course, in reality, in Fortran, the size that goes with an array is how big the array is, but there are actually plenty of occasions where that size isn't the one you're interested in anyway, and all kinds of complications. But the thing is, you don't want to have two sources of the same piece of information. So basically, takeaway message: any piece of information that you've got in your code or in a database or even in a file format that you're writing to disk, you want to have one piece of information in one place in such a way that you cannot accidentally use an incorrect version or an old version, in such a way that when you update it, it automatically updates everywhere throughout your program or database as soon as a change is made. And just generally try and make your own life easier by being in a situation where you can't have stale, old, incorrect, inconsistent data that you then have to deal with somehow.